All right, so here's a pretty cool little video clip of a wheel being thrown forward with some backspin. You can see it grab the ground and turn around. Kind of an interesting thing about this when you look at it is as the wheel comes in from the left, it's got this backspin, so it's gripping the ground, skidding and skidding and skidding. When it gets to this turnaround point right here, you can see it doesn't have any linear motion or motion side to side, but it's still spinning. So it kind of grips the ground and peels out. So it skids for a little bit as it peels out, continues to skid, and then the rolling sets in and it just takes off to the left. So we're going to take a little bit of a closer look at that. All right, so before diving into the nitty gritty of the mathematics of rolling and skidding, it's good to look at a couple just kind of conceptual examples. One case here would be that you've kind of launched a ball forward with a whole bunch of backspin, in fact, so much that it turns around. So in other words, the ball's being thrown forward with a ton of backspin. So skid, 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 the thing skids out here. Right here, the ball starts to turn around. So its translational velocity goes to 0, but it's still got the backspin. So it kind of grabs the ground and peels out and comes back this way. And then the rolling sets in at this point. Okay, so what's good to do is to kind of keep track of what's happening to both the velocity, the linear velocity, and the angular velocity. So the linear velocity, let's graph that in black. The linear velocity starts out big and positive. Let's choose positive to be to the right. So it starts out big and positive. It decreases as the ball skids. It decreases. It gets to the turnaround point here. So the ball slows, gets to the turnaround point. Now the velocity switches sign and comes back in the negative direction as it kind of peels out going this way. So it's like peeling out here. And then right at this point, the rolling sets in. So then boom, and then it just goes flat like this. So that it just rolls away at constant speed, right? Similarly, we can look at the angular velocity. So what's happening here is the ball's been given backspin, right? We'll define that to be negative angular velocity. And so what I'm going to graph here in red is the product of the radius and the angular velocity, or r omega. And what happens is the angular velocity is big and negative here. Now you notice the angular velocity slows and slows and slows down, but when the rolling sets in, it's still rotating in the same direction. So that means the angular velocity does not switch sign. So what happens is r omega will start big and negative. It will slow, getting closer and closer to 0. Slow. And then right at this magic point here, right where v equals r omega, that's when the rolling sets in. Right? And in fact, that's going to be the condition for rolling in all these cases. Right? So we'll take a look at another example. Here the ball is launched forward, but it just has kind of like a tiny bit of backspin. So what happens is it's skidding here and slowing down its rotation. So skid here. Now here it just so happens that it's not rotating right at this instant, but it's still translating forward. So it has linear velocity, but it doesn't have angular velocity at this moment. So this is kind of like throwing a ball forward here with no spin. So friction is going to cause the thing to start to change its direction of rotation, and it'll start to tumble forward. So it'll skid for a little bit, and then the pure rolling will set in here, and then off it goes. Okay. So what you notice here is the velocity, linear velocity, did not change sign. It's always going in the positive direction. It just slowed down. So if we graph the velocity, it starts big and positive. It slows down throughout this entire process, but then once the rolling sets in, then boom, then it just takes off like that. Right. If we look at the angular velocity, it started off big and negative because it had backspin. It slows down, it approaches 0, it gets to 0 here, then it actually switches sign and starts going the other way. Right, so that angular velocity starts big and negative, here's r omega, starts big and negative, goes up like this, crosses through 0, right, while it's still traveling forward, right, it still has forward velocity, but no angular velocity, let's say at this point. So nothing that special about this point except for the angular velocity just happened to have crossed through 0. And then a little bit later, then the true rolling sets in. So it's skidding throughout the entire process until the actual rolling starts. And again, that's at this magic point when V equals R omega, both in magnitude and in sign. V and R omega have the same sign once the rolling sets in. Final conceptual example here would be you give the ball a bunch of forward spin and then just kind of set it on the ground. So it doesn't have any linear velocity yet, but it's got like a boatload of angular velocity. So this is kind of like, peeling out with the Camaro in the parking lot. Okay, so you take off, you lay a patch on the ground here. So skid, skid, skid as it peels out, and then just boom, the true rolling sets in. Here, notice the translational speed or linear speed has started at 0. So if we graph the velocity, well, it just speeds up and then the rolling sets in. So we speed up and then boom, the rolling sets in. So it goes linearly upward and then it goes flat, right? If you look at the angular speed, all it's going to do is slow down. It starts with a big positive angular velocity. It's got forward rotation. So if we graph R omega in red like we were before, R omega is going to start big and positive and decrease until that magic moment when boom, the rolling sets in. Again, where V equals R omega. So I encourage you, when you start to set up one of these problems, just make a quick graph of what the linear velocity and what the angular velocity is doing. It'll just make it a little bit easier once you get into the mathematics. Look at an example of this, classic example. This is where you set a ball down with kind of top spin, but don't throw it forward at all. So you kind of let the ball peel out and take off and eventually begin rolling. So it says ball set down with top spin, omega naught, and no initial velocity because you just set it down. And what we're supposed to do is find the speed and how much kinetic energy actually remains when the rolling sets in. So again, as I mentioned in the last little clip, what's useful is to think about how the velocity and the angular velocity are going to evolve. So the velocity, well, it starts with no velocity, and the velocity is just going to grow and grow and grow until eventually the rolling sets in, right? Because it's going to kind of grab the ground and peel out, and then eventually the rolling will set in. So that the linear velocity is just going to grow and grow and grow, and then rolling is going to set in. It's going to go like this. The angular velocity, it starts out big and positive. So if we graph R omega, it's going to begin up here at like R omega initial. And as that thing grinds against the ground, it's going to lose angular speed. But since it's going to just continue to go forward, it's not going to switch sign. So it's just going to kind of come down like this and then flatten out. So that's what we can anticipate things looking like. This point in time is when the rolling is going to set in. Okay? So let's go for it. So what you do, we have to keep track of what the velocity is doing and what the angular velocity is doing. Well, so to keep track of what the linear velocity is doing, well, what governs how linear motion changes? Well, that's the forces. So if we look at F equals ma on this thing, right? So our force, as this thing's kind of grinding against the ground, there's going to be this, as the ball's trying to slip by the ground this way, the friction force is going to act like this, forward. So there's your friction force, which is mu times n, or mu mg. So there's our friction force. People get confused sometimes about, doesn't friction oppose the motion? Well, friction is actually what's making the ball go forward in this case. It is opposing the slipping of the surface of the ball against the ground. But that is actually acting forward. If you stop and think about it, this is actually what makes a car go forward in general. So you can use friction to help you move, and that's what's happening here. So if we set this up, we have the horizontal force. The only horizontal force acting on the ball is friction. So we have mu mg equals ma. Mass is going to slash out. And so it looks like our forward acceleration is mu g. So that's this rate of growth of the velocity or the acceleration. So we know that. And what we then know from kinematics is that velocity is like v initial plus at. But there isn't any v initial. So, right, there's no linear speed at first. So what we know so far is that the linear velocity is acceleration, which is mu g, times the time t, right? So the goal is to find the speed when the rolling sets in, but we just don't know the time yet when the rolling sets in. So what we need to do now is we got to keep track of how the angular velocity is going to evolve, because ultimately we want to see when v equals r omega. And so to handle the translational part of stuff, you do torque as I alpha. So the rotational version of F equals ma. Right? Rotational force is like rotational mass times rotational acceleration. So it's just the rotational analog. So what's going to happen here is the torque is being provided by this friction force here. So we better put like the radius of the ball. You know, here's r, the radius of the ball. So our torque is going to be friction force times distance, or mu mg times r. Force times distance is a torque, right? Then equals the moment of inertia, which for a ball or sphere, we'll have it be a solid sphere, is 2/5 mr squared. You can look that up, right? And then alpha. Now, what you don't want to do here, a possible mistake is, you may have seen earlier in mechanics class like a relationship like A equals R alpha. That's only going to be true once, like, if there was no slipping of the interfaces between the bottom of the ball and the ground. So it's not true that A equals R alpha, so don't make that substitution here, okay? So leave this as alpha. What's going to happen here is the mass will cancel. And so what we're going to be able to do is get the angular acceleration here ultimately. So, oh boy, let's see. This r goes away. That gets rid of one of these r's. So it looks like we get 5 mu g, all over 2r. That's the magnitude of our angular acceleration. Right. Now what we want to do here can be a little bit tricky. We want to look at what's happening with the angular velocity to kind of decide what sign this thing should have. So what you notice is the angular velocity needs to start big and then like decay. Angular velocity starts at omega naught and then comes down. So we really want to force this thing to be negative. We want that initial angular velocity to decrease. Okay, so you kind of want to play an active role here in thinking about what's happening. So we're going to force this to be negative. Right, because otherwise we would have it gaining or accumulating angular speed, which is not what happens. So you kind of got to be active in thinking about it in this case. So this is going to be negative, and so force this thing to be negative. And so what happens is the angular speed is going to evolve like this. Omega is omega initial plus alpha t. So omega is going to be, well, we're given the omega initial. Now we want to force this thing to be negative, minus 5 mu g over 2r. Again, if I don't force this to be negative, it's gonna, omega's going to grow, which is not what happens here, t. So there's that. So here's how the translational speed evolves. Here's how the rotational speed evolves. These things are happening independently, but then what gets them together is we set v equals r omega when the rolling sets in, right? So what we want to do is at this magic point where the rolling sets in, at v equals r omega, that's where we're going to get these together. So let's set v equals to r omega. So what we have is mu gt equals, now we got to set it equal to r omega, equals r omega initial minus r times this thing, which is just going to get rid of the r in the bottom, minus 5 mu g over 2t. So what we're going to be able to do here, notice the only like unknown is t. So what's neat about this is this is going to give us the time when the rolling sets in. So let's do that. So we're going to bring this 5 mu g over 2t over here combined with the mu g over 2t. So this is like 2 over 2 plus 5 over 2. That's going to give you 7 over 2. So 7 over 2 mu gt equals r omega naught. And so what we learn from this is that the time when the rolling sets in is going to be this. The time is going to be, well, we just got to solve for it. R omega naught, 2r omega naught. So bring the 2 over 7 mu g. All right. So then, so that's the time when the rolling sets in. Now what we can do with this is let's now then find the speed, because we're supposed to find the speed when the rolling starts. Well, this is the time. This here's the time. And so what we can do with this is just plug this back into the velocity equation that we found here. Okay. So what I'm going to do here, I'll just shift this over here just a little bit. So let's find the speed when the rolling sets in. So this is like t for rolling, right? Move this down a little bit. That's the time when the rolling sets in. So let's check it. So the velocity when we roll is going to be, well, mu gt. So mu g times this. And so that's just going to get rid of the mu g in the bottom. So it's going to be 2/7 r omega naught. Right. So that is our speed. That's the speed when the rolling sets in. Right. Final part of this problem is we're supposed to figure out, well, how much of the original kinetic energy does it have when the rolling starts? Because what's going to happen is you start with a whole bunch of rotational KE, and it grinds and grinds and grinds against the ground, so it's scrubbing away, making noise, losing energy, and then it's going to have translational and rotational energy at the end. So let's just check that. So what we need to do is get the KE before and the KE after. Well, so KE before, which is 1/2 I omega initial squared. So we can get an expression for that. So that's 1/2 of 1/2 of 2/5 mr squared. And then I need times omega initial squared. So I can get this expression. What is this? 1/5 mr squared omega initial squared. Right, there's the that is the initial that's the initial kinetic energy. Now let's get the final kinetic energy so that we can compare. KE final, KE after. Let me change that. KE after. Here, I'll block this off so it's a little easier to follow. There's going to be two things going on. There's going to be, the thing is going to be translating and it's going to be rotating. So let's do, here is the translational part. That's just 1/2 mv squared. 1/2 mv squared. 2/7 r omega naught squared. This is the translational part. So I'm going to write trans up above this thing. There's the translational part. And then we need to add to that the rotational part. So that's 1/2 I omega final squared. So that is going to be 1/2 of 2/5 mr squared. That's 1/2 I. And then we got to do omega final squared. Omega final, since V equals R omega, like V final equals R omega final, omega final is just going to be V final over R. So we can make that substitution here. So omega final squared is going to be V final over R squared. So here is our V final, right? And so then we'll square it, but then we have to divide out R squared. So our omega final squared is going to be this thing squared divided by R squared. So forget about the R then. So it's going to be 2/7 omega initial squared. All right, so let's wrap this up. So it looks like in each of these terms, let's kind of pull out what the common factor is just to make this look a little bit less intimidating. So KE after, looks like every term has 1/2 m r squared omega squared in it. So let's just pull that out of both of these. So we have 1/2 m r squared omega initial squared. That's common to both terms. I'm just trying to get it so that we can kind of write it all in terms of just some fraction. And then actually both terms also have a 4/49. So we can kind of factor that out too. So times 4/49. So all this mess is actually common to both terms. So this is identically the first term. And then the second term just has this, is exactly the same, except for this factor of 2/5. So you get a 1 plus 2/5. Right. Just trying to shrink this down so it's not so messy. So let's see. This is 5/5 plus 2/5 makes 7/5. So I am just going to change this right here so I don't have to keep going. 7/5. Right. Now we should be able to get this set up so that so the goal was to compare it to the KE before to find out the fraction that remains. So a neat thing, a way to make this easy is write this as, let's write it in terms of the KE before. So before, if we take this 5 out, we have 1/5 mr squared omega initial squared. Right, that's actually the KE before. I'm just isolating that. And then what we have to do is collect all the rest of the junk. So we've kind of taken care of that dude and that dude. And so then we just got to get the rest of this. So this is going to be 2/49, but then times 7. So it's, we can do a lot of simplification here then. So the 2 and the 4 conspire to make a 2. The 7 and the 49 conspire to make a 7. Oh, that's nice. So ultimately, this just ends up being 2/7. 2/7. So then, okay, so now if we compare, this is the KE after, is 2/7 of this expression. Well, this expression is the KE before. So what that means is that 2/7 of the initial KE remains. So 2/7, what's that as a percentage? I used to know my sevenths decimals. 0.286 or 28.6%. Of the initial KE remains. So it's scrubbed away a giant fraction. It's scrubbed away 5/7 of its initial kinetic energy.